¿Y ya llevas algún año sin nada? Pues sé que es una película.
Primero la exigencia. Pero si tienes siempre, ¿no?
Pensaba que había visitado. No, porque es que si o sea, ibas a acertar. Sí, creo que sí. Sí, creo que está.
Okay, so while they are fixing all these technical issues, let me make a couple of announcements. So you have the certificates on the table. So all of you which didn't pick up the certificate, please do it. Okay. And the second thing is that I don't know whether you know that we are going to move to another faculty to make the practice this afternoon, because there was no spare place here at the science faculty. So we are moving to the law faculty. So in order to go all together, so we will meet at the front door of the university at the quarter 2-3, okay? 2:45 at the front, at the hall. I mean, we are not going to wait for anybody because we are, I mean, we have to try to start on time. So please make sure that you will be at this time by the entrance, okay? And yeah, 2:45 here at the front door, okay? And we will walk together, okay? Yeah, it's 15 minutes walk more or less. Okay, it's a little bit far. More things. We would like also to make a photo for the conference, but we will do it at the low faculty, okay? So when everybody will be there. So please bring your, make your hair and yeah, bring your hair. We should have all new yesterday, right? Okay, so let's start. So it's my pleasure to introduce Jesús González Vázquez. So Jesús finished his PhD in year 2007. Already. He was supervised by Ignacio Salá. He did it at the Universidad Complutense in Madrid, also with the CNRS. Jesús Santa María, but it was the Complutense also only the Complutense. Okay. Then he moved to Germany, where he made a couple of postdoctoral stays with Professor González. In year 2010, he came back here to Madrid, to Spain, again to the Universidad Complutense in Madrid, but this time he was in between the Complutense and the CSIC with a Juan de la Cierva contract. And I have to say that he's one of the main developers of the algorithm behind the Shark. Okay? So he put much effort in this project, and well, his interests are basically electronic structure calculation on smaller and bigger molecules from now on. And he's also interested in femtochemistry, atochemistry, and control stuff. So this is so whenever you want.
Okay, so first thing is Juanjo for giving each here. It's really amazing that the quantity of people that is here. Also, I want to apologize for my accent because it's still very Spanish. I tried to improve it, but we have, especially staying here. So, what I want to try to teach you today is going to be in this week we are going to speak about the surface hopping methodology, but I put it a little bit more general. So the idea is that we have somehow to take into account quantum effects, but using semi-classical methodology. So this is a little bit the outline, what I want to show you today. So the first thing is why you need semi-classical. Probably you already know why, but I'm going to be very, very, very short here. Then, in order to understand how it works, instead to use huge molecules and very difficult, I am going to focus in some molecular models that are also the ones that I am going to propose you to use this afternoon in the practical session more this evening. Okay? And then I am going to show you how one proceeds when do semi-classical dynamics. So most of the things you already know a little bit, because I know Basile was explained, and also probably Cristina, the quantum part, and Pedro yesterday, the more classical part, no? But just a brief summary. The first thing that you need is to create initial conditions. You already know why. Then, ideally, if you're going to work with photochemistry, you need to calculate a semi-classical spectrum, and we explain what it is. And then with this, you can do the dynamics, okay? And the dynamics requires 3 steps, or 2 steps, basically. You have to solve the time-dependent Schrödinger equation with classical nuclei, and you have to couple this time-dependent Schrödinger equation with your classical movement. And usually, we are going to speak how to do it with surface hopping. And also, I'm going to speak a little bit about the problems of surface hopping and how to solve it, basically the coherence and everything. So this will explain everything about surface hopping. And afterwards, I will just give a little bit of flavor of what we can do with surface hopping in difficult cases, I will say. Okay, and then I'm going to go beyond models in this case. So I'm going to speak a little bit about methyl iodine, how you can use surface hopping in methyl iodine. That is not trivial. And also, I'm going to explain a little bit, very, very small here, about prebiotic DNA and things that you can do when the molecule is selected. Okay. Finally, some take-home messages and more or less so. I hope that it's going to be easy. So, why semi-classical? Okay. Even if I put Universidad Autónoma de Madrid, I am not from Madrid. The Spanish people that hear me know I am from the northwest, a region that is called Galicia. Okay. And one thing that we have in Galicia, and in fact, the inner part of Galicia, and one thing that we have in Galicia is water. Okay, usually we agree, we pay the price, and usually we have a lot of water. So I can imagine my energy landscape like water. So it's a region that you are going to fill with water. Okay, and then usually you already know, if you imagine this in this way, there are statistical methods. You can do a lot of stuff, no? So you want to explore the dynamics of this. You can, of course, explicitly follow the time evolution. This is correct. Or you can use statistical models. Probably you already know about the transistor state theory and its variational part, variational transistor state theory. This is when you work in canonical ensemble. If you work in microcanonical ensembles or the energy, there are an equivalent theory that is called RKM theory. I don't remember the initials. It's the initial of 4 people, but I don't remember that. Okay? And then there is another thing also that is called metadynamics. I don't know, do you hear about metadynamics? Probably you heard yesterday about metadynamics. Basically, what you do is what I explained here. You basically have your landscape and you fill it until you go to a place where you can live the well, basically. No? And this works very good. So why I'm here explaining surface hopping if you have all this knowledge, okay? Well, the problem is that we are in excited states. And then, of course, this is metadynamics. You basically put everything and then you check. And then we have leaks. So the water, if you go in the ground state, no problem. You can start to fill until you arrive here. Fine. But if we were in excited states, we have leaks. So if we are in this excited state, for example, we can go to another excited state here through this leak. I know that Vasily already explained you this because he likes a lot this type of diagrams. Jablowski diagrams. Okay. I am very bad with the names. Okay? So you can see, okay, you have a lot of processes and then you have leaks. So everything that you learn with statistical dynamics is not going to work very well, because all these leaks are going to destroy your statistics, okay? And then in this case, probably the only thing that you can do, or one of the things that you can do, is to do directly explicit time dependency. So to solve directly the dynamics. So you cannot use almost kinetics. I mean, you can try, but it's going to be hard. So how we solve dynamics? Okay, there are several ways. The best way is quantum dynamics of electron and nuclei. This you can do it for hydrogen, probably. Maybe if you go beyond that, it's going to be hard. Then, if you want to have more dimensions, let's say up to 5 dimensions, maybe you can do it by solving the quantum dynamics using the Oppenheimer approximation with the Born-1 expansion, if you want. But at the end of the day, the electrons are treated in a different way because you previously calculate the potential that you're going to have. Okay? Maybe you can do, if you are lucky, to 5 dimensions. There are approximations, no? So you already know the 2 main approximations in quantum dynamics: MCTDH, okay, and initial multiple spawning. If you can say this is quantum dynamics, that is a little bit difficult because in the moment that you have a lot of trajectories, they spread too much. You have too many degrees of freedom, and it's very hard to maintain the communication between them. But you can do it, but it's going to be hard. And then there are another type of system, another type of methods that are usually called mixed quantum classical dynamics methods, okay, where basically your electrons, your nuclei are going to be classical particles, and the electrons are going to be quantum waves. And this is what I am going to focus on. Okay. So, where I am going to explain it, I am going to focus into models that we used some time ago. One is the sodium 2 molecule that you can say is not very interesting, but you can use it for for understanding the things. Okay? So in this case, what you have is like 3 potentials, and they are coupled to the dipole moment in such a way that the first one is coupled with the second one, and the second one is coupled with the third one. And this is more or less the shape of the dipole moment. This is one model that we are going to check. The other one, what I'm going to focus more, is something that we did a long time ago, 11 years already, okay, that is bromine iodine, that are potentials that are modeled in the literature. Okay? How it works, you have 3 states, the ground state, and then you have 2 excited states across. Okay? In such a way that, in principle, you excite with the dipole moment to the state 2, so to the red, okay? And then through no adiabatic coupling or intersystem crossing, whatever you want to call it, you can go to the blue. Okay? And then you have this dynamics going here, and then you can have here a conical intersection that who knows what it's going to do. So I am going to try to explain everything in this model to understand how it works and what we can do. Okay? So this is the most, I am going to use most of the times this one. So what you have to do. The first thing you already know also is you have to mimic the initial vibronic state. In my case, in principle, there are several ways, depending on what you work. Some people say it's better if you do a dynamics that has into account an harmonicity. You run the dynamics for some time, and then you just take a snapshot of this trajectory and send it to the excited state. But usually, I would say I don't like too much the idea, because the main problem is that in classical dynamics, usually most of the time the trajectory is in the turning point of the potential. But in quantum dynamics, what you have is totally different. So the probability to find the particle in the turning point is very small in comparison with the particle to find the particle in the middle. Of course, when you have a lot of degrees of freedom, probably this is going to be blurred. Okay? It's going to be difficult that you can manage that. Okay? The Wiener distribution is just a cheat, okay, that you basically want to know the probability of finding a particle in a position and a momentum. This is not possible, but you can try. Okay? And then if you try to do it for the v equals 0, you have this shape. So the maximum probability is in the middle, then you have another probability here, another probability here. Okay? And then if you have this wave function, you can sample it. This means that I can create initial conditions, so I can create displacements in momentum and coordinates such as average, it's going to give me this behavior. How I do that? Okay, I start to check, and then I just use random numbers, a lot of random numbers, and I accept some of them, reject the other ones, and then I have that most of my initial conditions are in the middle, and then I have another ones that are a little bit in the outside of the webpack. Okay? And this is something that I can do. And I can do it for all the normal modes, let's say. Okay? So that I will have a sampling for every normal mode, and then I can combine them. I have a sampling in position and momentum for all the degrees of freedom. Okay? So I can do this. I can try to do it also for v equal 1. This also works. The problem is, as I say, I am cheating, and then I have some place where I have negative probability. Okay? That in principle is not possible. Basically, in the nodes that I have just in the middle, I have negative probability. Okay? In the v equal 1, this is not very dangerous because I still can check, and then I will have a distribution where I don't have any trajectory or any initial condition just in the center, because this is forbidden. So there are no probability there. Okay? And this is something that one can do. And this is basically what we are going to do in order to mimic the vibranic state, okay, the first vibranic state. I am going to focus in the v equals 0. But once that I have these initial conditions, I have the v equals 0. So I already construct the v equals 0 of my ground state. Okay. And now, tell me.
Yeah, good question. So the wave function that appears in the integral of the different distribution, that those are vibranic wave functions, right?
This is the vibrational wave function for the V equals 0 or the V equal 1 in the ground state of, in this case, IBR. I do it numerically in general. So this is a loss of time when you work in harmonic approximation because there are analytical solutions. And the trajectory is going to take much longer than to do this. Okay, so I don't care too much. And the good thing is that I still didn't publish anything, but in principle, if you do numerical, you can have some sort of an harmonicity included. But let's see. Okay. So next thing, now we have the V equals 0, and we want to know how these trajectories or how this V equals 0 wave function is going to be propagated in the excited state. So the first thing that we need to know is how we can go to the excited state. And this we can do it using a semi-classical spectrum. What is the idea behind semi-classical spectrum? I am going to start from a vibronic level included in the sampling, V equals 0, V equals 1, whatever you want. And I am going to, so I have here my ground state and my wave function, okay? And I am going to assume that my final states in the electronic set states are not going to be quantized. This is going to be true if you have something like this. For example, if you have a continuum, basically in the continuum, all the energies are allowed. So this means that this is totally true. In generally, when you have multidimensional systems, it's going to be also true, because the minimum of the ground state and the minimum of the set states used to be very far away. And then this means that you have a lot of energy that you can put in the excited state. So you are going to be very high in the vibrational levels, and then they are going to be a quasi-continuum of states. Okay? Then, once that I have this is something that I assume, as I said, I am going to do calculations for every initial condition. So, and I'm going to check the probability. So this means that I took, this is going very fast. So this means that I took my trajectories, and for each one of the trajectories, I check where is the excited state. So most of the trajectories are going to be in the well, as I explained. So for example, in this case, I have 3 trajectories that are in the well. I check where is the excited state. I also check what happens in this region with these trajectories that I have in this region or in the other region. Okay? So I check everything, and I evaluate the probability of being excited using the oscillator strength. So the energy of the final state minus the energy of the initial state for this trajectory times the dipole square. Okay? So this basically means that I am going to have a region, that is my wave function, and I'm going to check how this region behaves in the excited state without knowing if there are here vibrational states or not. I am assuming that there is no vibrational states. Then what I will have is an energy region in the excited state that corresponds to the energetic region in the ground state, and this is going to be my expression. Okay? Very, very, very simple. The only thing that you have to do is single points for every initial conditions and check where is the excited state for every initial condition. So let's see how it works. This is with Jordan. So this is the quantum result. Okay? Since I am, sorry, this is sodium 2. Since I am in sodium 2, here this is not a dissociative state. It's a bound state. So I have here a lot of vibrational levels. And if I do the quantum result, I have a lot of lines, each one for one vibrational level. Okay? If I try to do the more crude approximation, that usually is what you do, you just check what happens in the Frank condom and then you put a Gaussian. Okay? If I try to do this, I have this black line. So this is basically the result of my equilibrium state, and then I just put a Gaussian, and that's all. Okay? If I do it with semi-classical spectrum, in this case, it's not a big difference. The only thing that you see is that, okay, this is a little bit higher, but it's more or less the same. So in this case, for example, there is not a big difference if you do it in the crude approximation, just use the Frank condom and put some phenomenological Gaussian, or if you do it using a semi-classical spectrum. Okay? What happens in Bromon iodide? Okay, this is the quantum shape. Now you can see that the lines are much, much closer, because now I am in this region, okay, And this region, it has some, the vibrational levels are like, you have more in the continuum part. If I do the same than before, I have this black line that's not very nice to see, but basically this is the equilibrium. And then if I put a Gaussian, I can try to cheat and put a little bit higher the Gaussian or whatever. But if I do semi-classical without cheating, I get the red curve. So you can see that I am having exactly the spectrum. All the vibrational levels are there because I am now using a lot of initial conditions. So I am sampling the ground state, okay? I can try to do it also for the V equal 1, and this is the result. So this is the V equal 1. If I start in V equal 1, if I try to do it in this crude approximation, it's not possible because I only have the equilibrium. So I will have the potential or the spectrum just in the node. Okay? If I use a semi-classical spectrum, I have these two peaks that are very similar to these two peaks that you get in the quantum dynamics, okay? In the quantum model. So, basically, this is a way systematic that you can reproduce the spread of the wave packet or the spread of the spectrum without using a phenomenological Gaussian and say, okay, this is due to temperature or whatever. You don't care to do it vibrational, to calculate your vibrational level, to mimic it with sampling, and then for every trajectory or every initial condition in this sampling, you check where is the exact state. Okay? Easy. It's very easy. Okay. Also, you can use this spectrum now to select which trajectory you are going to run. And this depends a lot of what you want to simulate. Okay? Because nowadays there are a lot of technology that you can use. You can use nanosecond technology, and this will mean that basically you have only one energy in your laser pulse. So this means that you have to select around a single energy, because this is what a nanosecond laser is going to do, or what a sunlight is going to do. Or if you have femtosecond technology, for example, you will have a width in your laser that around 0.1 eV maybe. So you can select, you have to select around 0.1 eV, because this is the experiment that you want to simulate or the thing that you want to simulate. If you use, for example, attosecond technology, that in the case of this strong, this very low excitation energies is not available, and it's not going to be, I think. Then in this case, you have bandwidths that are around 5 EVs, 10 EVs. So then you can like put all the spectrum at the same time. Okay? So depending on what you want to do, you have to select from this spectrum which trajectories are going to be exact. Okay? But it's just another stochastic check. You just check, okay, which is the probability of this spectrum? Random number. It's lower, I took it. It's higher, rejected. Next one. And you do the same all the time. Okay? Okay. So for example, here there are some real examples. Okay, this is a molecule that is sort of a peroxide, and then you have here the spectrum. This is the CCF, this is the CAS-PT2. And for example, if you want to select the trajectories around 4.5, 4.7, because this is 266 nanometers, that is what they have usually in the experiment. No experiments usually have the 100 nanometers, and then all the harmonics. So the first harmonic is going to be 400, and the second harmonic is going to be 266. So then you select trajectories only in this region. This is, for example, in the case of this peroxide. And I saw that Emilio was showing you also that he was using automaking for this molecule, that we were doing excited states together. And then, for example, if you use this molecule, you have all these initial conditions, and then this is your spectrum. So now you have to select wherever you want to do the dynamics. Okay. Okay. So these are two examples of big molecules. Okay. So with this, what I have is the initial parts. I know where I start, and I know where I am arriving to the excited state. Not all the trajectories are allowed, only the ones in an energy range. and I just select them to run. Typically, I have to run like, to put some numbers. Here it's going to be smaller, okay, because you have only 1 degree of freedom and it's more very easy to sample, but in general, I run like 1,000, maybe 2,000 single points. And from 1,000 to 2,000 single points, depending on the width, I can get between 100 and 200 trajectories. Okay? If I want to have 1,000 trajectories, then I will have to run 10,000 single points. Okay? Roughly. In systems with 5, 6, up to 10 atoms, let's say. Beyond that, I am not there, okay. I don't know if I want. So now, once that we have the initial condition, geometry and velocity, and the excited state or the electronic state where we want to run, the next thing that we have to do is to run the dynamics, okay? And then what we are going to do is to do a semi-classical propagation where the electrons are going to be quantum. And I am going to solve them using the time-dependent Schrodinger equation. Not the time-independent, the time-dependent, okay? So this means that I'm going to solve this equation. The nuclei are going to be classical. So the nuclei are going to be solved using Newton's equation. Okay, so the important ingredients here are Hamiltonian. I need to know the Hamiltonian at every time. And gradient. I need the gradient to run the semi-classical path. Okay? Well, so let's see how we can solve the time-dependent equation, because it's not trivial, okay? So if we have one potential, it's very, very easy. The Hamiltonian is just an energy. This energy can change with time, of course, because you are moving the classical trajectory, and then the energy is changing with time, because when you move, there is a new potential energy, okay? But at the end of the day, you just have to integrate this thing. And let's see how it works. Imagine that I am in the ground state, a little bit displaced of equilibrium, okay? And now what I am going to do is I'm going to run the trajectory in the ground state. Very, very easy. Just check. Okay? For you, this is trivial. This dot is going to be where is my trajectory at every time. Okay? And here, what I am going to put you is the population. Since I have only one state, I hope that I will have 1 in one state and 0 in the other. Now, I am going to put an extra ingredient, that is the phase. Because when I solve this equation, I am creating a phase. Okay? So let's see how the phase evolves. Because for me, this is time-dependent, a Schrodinger equation. So this is quantum. So the phase is important. Okay? So let's see also at the same time how the phase evolves. In this case, the energies are around minus 1.5 eV. And this is what it's going to give to the phase. And this is reflected in the color code. So this is my trajectory. So it starts to move in the region. And you can see here how the phase changes. You start at 0, and then you go to pi, then you minus pi, then 0, pi, minus pi, all the time. Okay? And this is the phase. So you can see here that my phase is changing very rapidly. Tell me.
When you're talking about the negative energy and you're talking about the simultaneously with the phase, then how it is negative energy impact to the phase? Because it means nothing.
Well, what means something is the relative phase. Okay, yeah. Here I am cheating a little bit. But in this case, that doesn't matter. You can put negative energy, because I can put here an energy that is negative, and I will have a phase. Okay? Because this is changing with an exponential. And doesn't matter if I put 0. I mean, if I put 0, of course, it's not going to change.
When we are not giving something, energy to the system or any particle, anything, then
no, but
how it impact, how it could we change the phase?
Because you can, okay, first thing, the important thing is not the absolute phase, even if I am speaking here about the absolute phase, okay? The important thing we will see later is the relative phase. Okay, the relative phase means that you have two things that are separated by an energy. And what you have to check in reality is the phase given by the energy difference. Okay, this is the important thing. But mathematically, doesn't matter if you do an absolute phase. The only thing that you have to do is to shift your energy. I can shift my energy. I can put my zero here, and it's going to work also. Doesn't matter if I put my energy here. In fact, some of you probably are used to quantum chemistry calculation, and usually my energy is minus 200, minus 300, in my case, minus 7,000. Okay, this is the absolute energy. Who cares of this absolute phase? You can put it in your propagation, but doesn't matter, no? Here, in order to explain you how it works, I put it. And the only thing that I am saying is, since my energy is very far away of zero, my phase changes very rapidly. Now, you are telling me, doesn't make sense if you have a negative energy.
Yeah.
Well, it's not true, no? Why do you think this is not making sense?
When we did not provide anything or no energy, then how we say that something will be
This
changed?
is not no energy. This is my potential energy. My potential energy is changing. If it's negative and changing in negative, doesn't matter. I can change it between 1 and 2. I can change it between minus 1 and minus 2. The only difference is that if I change it between minus 1 and minus 2, my phase is going to be negative at the beginning. If I change it between plus 1 and plus 2, my phase is going to be positive. It doesn't matter.
But I think
It has no physical sense.
Negative energy doesn't have any sense.
Physical sense. Okay, let's say it in this way. Doesn't have any physical sense. Okay, but mathematically, it's correct.
Mathematically,
Okay.
we can
Afterwards,
write what we
I will
want.
explain you what makes physical sense. That is not this phase. Okay, but now let me explain mathematically. It makes sense. Okay, I can do it. It's not a big deal. Afterwards, I will explain you what makes physical sense. Okay. Okay. So, of course, this is because my energy is here. So the phase is changing very rapidly. Now, if I do the same in the excited state here, now my energy is very close to zero. So this means that my phase is going to change much, much slower. And then you can see here that with time, this energy, this phase is changing slower, okay? Because I am closer to zero, okay? In fact, when I am very close to zero, the phase is almost zero, or is almost constant during the whole propagation, okay? Mathematically, it makes sense. This is what should happen. Now, if I compare the two situations, what I have is, in the highest case, I have a phase that is changing rapidly. In the other case, I have a phase that changes very slowly. Be careful, because the phase is not changing in a constant way, because my nuclei are moving. And the phase is something instantaneous that happens with the energy at this time. So there is a different phase depending on the time, okay, of my propagation. Okay. So, how we solve this? Well, the first thing that we have to do, we all know quantum dynamics, and you are going to have the slides, okay? The first thing that we want to do is to expand the wave function in a basis. In general, okay? This basis in principle is going to change. This is an electronic wave function, but it's changing because the nuclei moves. It's changing because it's electronic. And in principle, it's changing because I have a time dependence. Okay? So the wave function in general can depend on the nuclear position, electronic position, and the time dependence.
And when we are talking about nuclear position, and we say we are with respect to negative energy, then what we understand from this picture?
Let's see it. Because afterwards, I will give you a ton of questions. You can ask me whatever, okay? Now, please just accept it for 1 second, okay? Now I'm going to solve this equation, and this means that I have to know how is the change. I just drop the index with this here. I have to calculate the time derivative of the wave function, and this has to pass the time derivative of the coefficient that I am using to expand the wave function in my basis, and the time derivative of my basis. Okay? So using regular quantum mechanics, I will just multiply by one of the wave functions, another one in principle, on the left and integrate over the nuclear coordinate, because in principle this depends on the nuclear coordinate. Okay, and then I have here, if my basis is orthonormal, something very recommendable. Okay, then only the beta factor will survive, because I have here an integration of beta alpha. So this is orthonormal. And then here, what you have is basically the integral of the time derivative of my electronic wave functions. Okay? And of course, in the other part, you have the integral of the Hamiltonian. So let's see how it looks like in a very simple way. If I go to just make a small rearrangement, I just have a matrix here that is given by the non-adiabatic couplings or the time derivative couplings you're going to call it. Let's call it not time derivative at the moment. Okay? And the Hamiltonian matrix. Of course, at this moment, and it's what people usually do, and it's what I am also doing. If I select these basis functions as the eigenfunctions of the Hamiltonian at every nuclear coordinate, then this guy is just the electronic energy, and it's diagonal. Okay? And then this guy is how this electronic wave function changes because of the parametrization, because I am selecting a different electronic wave function for every nuclear coordinate. So this is going to be related to how the eigenstates of the Hamiltonian, of the electronic Hamiltonian, change with the nuclear movement. Whereas this is going to be diagonal in the regular, let's call it adiabatic approximation. Okay? Okay. So this in principle can be related with the ACME. In the special case where the time dependency of the electronic wave function is only due to the nuclear movement, this means that I only have a dependency because my nuclear moves, and then since my nuclear moves with time, then I have a dependency in the electronic wave function with time, because I am calculating for every nuclear distance. Okay. In this special case, only in this special case, one can use the chain rule to make the time derivative. This means that my time derivative here, I can do it as a time derivative with respect to time. It's going to be the same as the derivative of r with respect to time, times the derivative of the wave function with respect to r. And this is basically, this part is basically the non-adiabatic matrix element that I think Vasily already explained. Okay? I want to clarify here that what we need in semi-classical dynamics is not the non-adiabatic coupling. It's the time derivative of the wave function that you can extract in some specific case from the non-adiabatic coupling. Okay? But this is not what we did. Okay? So we can calculate afterwards, this is what we're going to have. So you have the non-adiabatic coupling, you can calculate the time derivative as the scalar product of the velocity of your trajectory times the non-adiabatic coupling. Okay? But what we put in the dynamics is this: the velocity times the non-adiabatic coupling, not the non-adiabatic coupling. Okay? Here, no? But as I say, we really don't need the numbers, no? And if you are, and the numbers are cheap, are expensive. So if you want to calculate the non-adiabatic coupling, it's going to take a while. And in principle, you don't need it. You just need the time derivative. So one possibility is to use finite differences. That is what I do. So basically, I say, okay, my derivative of time of my wave function is just the wave function at time t minus the wave function at time t minus delta t divided by delta. This is just a simplification. And if you basically develop these equations, what you get is that, okay, you have two terms, one term where the two wave functions are given at the same time, and another term where you have to do the overlap between the wave function at time t and the wave function at time t minus delta t. So basically, you need, this one is going to be orthonormal, pardon, sorry. So this is delta beta alpha. And then what you need to calculate is the overlap between the wave function at this time and the wave function at the previous time. And with this is something that you have. I mean, you have the wave function at this time, and you have the wave function at the previous time. So this is something that you don't need to calculate extra. It's there. Okay? So in that sense, you don't need to calculate the NACME, and it's simple. Okay? So this is what I am doing. Of course, it's a finite difference approximation. That's all. Okay. So, important things of this solution. The time-dependent equation is to solve a wave equation. So this means that this is invariant with respect to the unitary transformation. For example, in my model, IBR, I use this model where I have these two potentials that are coupled. This is so-called diabatic potentials. Okay? But of course, if I try to diagonalize it, I will have a coupling and I will have this situation. But you can see that the main difference is that in the region of the coupling, okay, now this potential makes this and this potential makes this. Okay? This is the adiabatic. Well, in principle, if you solve the time-dependent equation here or here, you get the same result. Because this time-dependent equation is invariant with respect to any unitary transformation. In principle, it's easier to solve it here. Because here the NACME are very small, and you put all the couplings in the potential part, in the Hamiltonian, okay? It's not something necessary. You can try to solve it here, and it will also work, okay? But here also, so doesn't matter. You can solve it in any of them. So this is a very good thing, because then we can solve it in the one that is more convenient for us, the one that is easier. Okay? Well, let's see what happens if I advance a little bit more the trajectory. We saw before that I have a phase. Okay, I am running the trajectory here in the region, and then I am going to be close to the other potential when I arrive to the region. No? What is going to happen then? That the two wave functions are going to be coupled, and then I will have some probability to have population in the other potential. So I will see that in the region, my population of the other state increases. And here is the important thing. Since the two energies are very, very close, the phase of the created population in the other electronic states is going to be very, very similar to the phase that I am running, because the energy difference is zero. And here is what I am trying to say, that what is relevant is not the phase, it's the difference of the two phases. So I have a phase, because I am running here, another phase if I will run here. And the difference between the two phases is what is important. If these two phases are very similar, then I will have more probability to go to the second state. So this what basically means, or to go to the other state. This what basically means is that in order to have transition, you need two ingredients. You need coupling, and you need degeneration. Okay? And this is reflected in the time-dependent equation. When you solve it, so if you solve all the phases, depending where you integrate in the BRA, you can have, even if you have a huge coupling, if one oscillates very fast and the other oscillates very slow, the integral is zero. This means that you cannot go to the other state, even if you have a very, very big coupling, okay? Because they are out of phase. Okay? So here the important is the relative phase between the two potentials. So if I create another state here, I should create it with the same phase or a very similar phase to the state there. Otherwise, that is the region here, no population transfer. Okay? In order to have population transfer, you need coupling and degeneration. Okay? Good. So this is concerning the time-dependent equation. The question is, okay, up to now we already see how it works. We can couple the time-dependent equation with the nuclear movement. It works, but we need the coming back. So we have at the moment one ingredient. When the nuclear moves, the time-dependent equation is affected. But we need an extra ingredient. What happens to the nuclear dynamics when there is a transfer of population. Because somehow it has to affect also the nuclear dynamics. It cannot be that I have a nuclear dynamics that affects the time-dependent Euler equation, but my time-dependent Euler equation doesn't affect at all my nuclear dynamics. Okay? And there are several ingredients of how you can do it, how you can do the back, how you can do the effect of the nuclear dynamics in the of the electronic dynamics in the nuclear movement. Okay. So as I say, I have the Newton equation, and then the first possibility is to use error test. This means that my nuclear dynamics is going to be affected because I am working. My energy is not the energy of one state, but it's the energy or the expected value of the energy of my electronic wave function. This is one possibility. Another possibility is surface hopping. You say, okay, I am going to run in a single potential, not an average potential, okay? So I am not going to consider the energy of my wave function. I am going to run in a single one. So my energy is going to be the energy of one potential, but then I am going to evaluate what is the probability of leaving this potential. So which is the probability of leaving this potential? And this is given by this equation. So when the wave function or the coefficient of the potential alpha is leaving, this means decreases, then I have a probability that is not zero to leave this potential and go to another one. And this is basically what surface hopping does. Still, the way to do this is by solving the time-dependent equation again. So this means that this derivative is going to be only zero, only non-zero, if I have the degeneracy and coupling. The same here, okay? Because here I am running with this guy and the same, okay? Let's see an example. So imagine that I have a wave packet and I have two surfaces, okay? Both are dissociative, very, very easy. So if I have a wave packet, probably Vasily already gives something similar to this. What happens is my wave packet goes to there. And now there is a crossing. So if I do quantum dynamics, 2 degrees of freedom, everything well done, then I will create 2 wave packets. One wave packet continuing in this potential, and the other wave packet goes to the potential. Since the red potential has a bigger slope than the blue potential, then this means that this wave packet at the end is going to be closer to this point than this wave packet that has more kinetic energy. I don't have wave packet. I have trajectory. Okay. The same at the beginning. I am going to run in this potential, and now when I arrive to this cross, there are several options. Option 1, I create a potential from my wave function, and I run in this potential. So then, since I am mixing these two states, I will have an energy, effective energy that is in the middle. Okay. This is called Ehrenfest. This is called Ehrenfest dynamics. Okay? And I will arrive somehow here. Now, another possibility. I arrive to these points, and I will stay in the blue potential, since I have a very small slope, or I can stay in the red one. In the blue, since I have a very small slope, I will finish somehow here. That is before the Ehrenfest result. Okay? If I stay in the red potential, then I will stay here. That is above or after the Ehrenfest result. Okay? This is called surface hopping. These are the two possibilities. Okay? The trajectory can only be in one potential. Okay? Not in two. So I am going to focus in surface hopping. Because if you remember how it works, the wave packet, you can think that in principle it's more similar, no? Because my wave packet was divided, and I don't have wave packets here in the middle. The one that was running here have one gradient, the one that was running here have a different gradient, but nothing like a middle gradient. There are ways to solve it in the NFS, but they hire me for surface. So then I am going to speak a little bit more about surface. Okay. So this is the two solutions: NFS to stay in the middle, surface hopping to decide in which one you are going to run. Okay. So how we do that? We know already that we can solve the time-dependent equation. We know already that we have somehow we can evaluate the probability of leaving this state. And then, in the case, the code that I am using is based in the Shark theory or in the Shark methodology that was proposed in 2001. 2011. In 2011, just when I arrived from my postdoc, and it was a collaboration between Ignacio Solá and me here in Madrid, and Leticia González and Philip Marketal and Martin Richter in the Universidad of Jena. Not Vienna, Jena, very small town. Okay? So then I will have this energy, in principle, and then I will have two couplings, because I can transform these couplings when I adiabatize, so when I diagonalize this Hamiltonian. Okay, I have to include this diagonalization also in the non-adiabatic coupling charge. Okay, so then I have two possibilities. One possibility is just the rotation due to this unitary transformation for the non-adiabatic coupling. And another thing is how fast this rotation might have changed. Okay, this was the original idea. In such a way that we can have non-diagonal elements in the Hamiltonian, but they still work in the adiabatic representation. I will explain you why. So as I said, in the case of time-dependent equation, you don't need to do that because it's invariant with respect to the unitary transformation. So it doesn't matter if you do it in a Hamiltonian that is coupled or in a Hamiltonian that is diagonal. It doesn't care. It's going to work because it's invariant. Okay. Now, in semi-classical dynamics, you have to do it in the same representation that you do the surface hopping. And we already saw that in principle this is the adiabatic one, because we saw that the wave packet, if you have a wave packet, will spread in two, and this wave packet is going to be slower, this wave packet is going to be faster. So in principle, you want to do the dynamics in this representation where the wave packet spreads. Okay? So you want to do the semi-classical dynamics in the same representation of the surface hopping. This is compulsory. And in principle, the surface hopping, according to Julie, has to be done in the adiabatic representation because the surface hopping is a trick. This means it's not something real. It's a method that we use to treat this type of systems, but it's not an observable or something like that. Okay, so this means that in principle is not invariant with respect to the representation. If it was not a trick, it doesn't matter. If you use quantum dynamics and everything is treated in quantum mechanics, it's invariant with respect to the unitary transformation. You will have the same observables if we run in uncoupled surfaces or you run in coupled surfaces. You will have the same result. But this is not quantum mechanics. It's a flavor of quantum mechanics. Okay? It's a trick. So this means that in the case of surface hopping, it's not invariant. So you have to do it in the representation that is more convenient for you. And truly demonstrate that the best one is the adiabatic. Okay? In principle, to do this, you will have to put this derivative here, and calculate all these probabilities. There are alternatives because this is very hard because you have to maintain the phase of the U matrix, and it's really hard. Okay, so there are alternatives that are surface hopping alternatives that are based on the flux. Okay? And I will explain you one of them that I think is the easiest one to understand, and in fact is the one that I have implemented. Okay? So there are two possibilities. I'm going to focus on the last one that was developed by Dmitry. And this is the one that I read. I don't know if they used it before or not. but I found it in this paper as a step outside the paper because it's very useful. Okay? And the idea is that the surface hopping, if you want to go from state alpha to state beta, you have some constraints. The first thing, the density or the population of state alpha has to go down. So this is getting by this Heaviside formula. So if my wave function or my population in the potential where I am is not going down, the probability to live is 0. The population of the potential that I am checking has to go up. This is this Heaviside. Okay? Now, this is normalized by the density of the state where I am. Here you have the going down of the potential where you are, and here you have the probability or the going up of the potential where you want to go, divided by the rest of the potential. So it takes into account the rest of the states also. Okay? And let me show you just an example how it works. So again, I am going to do the same. I start my trajectory in this potential, I let it run, I follow the phase, and we already know that in the moment that the two potentials, the red and blue, are going to be very close, in this moment I am going to have a change of population. So this means that this flux is not going to be 0. Okay? Then I have this exponential population here, and then I decide, I stay in the same state or not. In this case, for example, I decide to change with the stochastic algorithm. So then, when I pass this state, the population of the state of the blue state increases, the population of the red state decreases, and now my new state is the blue one. And the phases of the two states diverge again, because now the two states start to be very far away, and then they oscillate at different phases. So all the integrals are going to be 0. So you cannot change population anymore between the two states. Okay? Of course, it's not the only possibility. I will have another trajectories, like for example this one, okay? Where my random number is nicer with me or not. This depends on your like, depends on your experiment. You always want to have the experiment result. And then in this case, for example, I feel the other potential, so I have an increase. But in this case, for example, my stochastic algorithm decides to stay in the red potential. So then my population in the blue goes down, my population in the red goes up again. During this period, the phase or the change of phases between the two potentials was exactly the same. And this is why you have this change of population. Okay? They told me a break, so maybe it's a good time to break. How long is the break?
5 minutes.
5 minutes break. Okay. And then I will explain you how to do surface hopping with a little bit more details. Okay? ¿Este agua se puede mojar o? Agua, es cold. I will say the opposite.
Hace calor, ¿verdad?
De calor.
No, calor.
And I was like, what the fuck? And I checked here. It was like self-check. And so, I did with my address. So he died. There's like another place because the third time and it's my swimsuit. I need to have it. So, and because they gave me my grade plan, so it's just like I can change my
Best of price.
No, for example, in the case of quantum usually where nuclei and electrons are you have this equation when you put 1 divided by r, and only when they are separated you have 0 energy. And then in the moment that you put it together, you have something extra. So the energy goes down. It's potential energy. I am talking about kinetic energy. I am speaking about potential energy.
If you take like
for example, then it's more stable. I said the potential energy doesn't happen in the
nice relationship.
Vale, perfecto. Yo le diría, claro, que el cambio de... Yo veía justo eso, veía que el cambio era rapidísimo. Arriba no me vale,
podría
en random sí, que cambia todas las condiciones de... Claro. Sí, sí que encuentra
Tienes que calcularlas para tener la control. Esas cosas. Después una raíz estocástica.
A ver, que no te dejan ni respirar, ¿no?
Yo respiro. Okay, let's continue. Okay, so let's
Déjame preguntar otra vez, a ver si algo está todo bien.
No va a regresar a casa.
Okay, so let's go to the quiz. But again, now that all of you are here, we have found these keys on the floor. Right? So do you recognize them?
Who is coming by car?
El llavero del Atlético de Madrid. Okay, if you know somebody who
Sufridor. Okay. No? So let's move, okay? Okay, please. Okay. Up to now, I explain you how the people usually do the thing, and I do because it's the way that most of the times you can afford. The other way, probably you cannot afford it. But in principle, the surface hopping, the only thing that does is taking into account a Hamiltonian, and then this Hamiltonian, principle, what change of phase, and then this phase you can use it to evaluate the probability of being another state. Okay. So very easy. So regularly, in my case, for example, I like a lot quantum control, and then in quantum control, what we use is laser pulses. Okay. So one of the things that we want to show using this discharge method is that you can consider also laser pulses. And for example, I am going to put two examples. One example that where it's not really necessary to use this methodology. You can use whatever, it's going to work. And another example where it's necessary. The first example is an impulsive regime. So what happens if I put in my Hamiltonian a laser pulse? What is going to do the laser pulse? Okay, the laser pulse is going to have an amplitude and then it's going to have a frequency. And this frequency, in principle, you choose it such as the covers this energy difference. So this means that this frequency somehow is going to mimic the resonance, no? Because it's going to give you an extra phase in your amplitude, such as the phase of this state plus the phase of the laser is going to be very similar to the phase of a trajectory in this state. So you are going to somehow induce the population by the frequency. Okay? So how it works? I am going to put a laser pulse, and then I have to diagonalize at every time step in principle. So this diagonalization at every time step is going to be different, and then I'm going to create an extra phase in this region, such as my phase in this potential, my phase in this potential are going to be very similar. And in this moment, in the moment that they are very similar, I can jump. So my surface hopping can say, okay, now you can go to the first step. And I can consider the laser part explicitly. Why nobody uses it? I mean, come on. I am in a model, so I can do it. But I know that, I don't know, 90% of my trajectories, I'm not going to jump, but I still have to run them. Okay, so it's really expensive to do this. You can do it in special situations, but in general, you don't want to do this. Okay? It's implemented, but I think since 2010, so 10 years ago, I never did it. So in fact, I don't know if it's totally functional at this moment, because I think I never used a laser pulse in a long time. Okay, but the principle is possible. Okay, what I want to show you here is that it's possible. And there are some ways that, for some situations where it's very, very important. And I want to, okay, this is the result. So I have my state here. Okay, this is the ground state. My laser is able to couple this state with this state. And then I have another state that crosses in this point, no? So this is the result of quantum dynamics. So in the moment that you turn on the laser, the population will start to populate the state, the red state. Okay? And then after some time, part of the red of the population of the red state is going to the blue state. This is the result of quantum dynamics. I have to say that in 1D, quantum dynamics is faster than semi-classical, okay? And it's exact as semi-classical approximation. So I am doing stupid things here, because in principle, if you have 1D, you can do it in quantum dynamics, it's going to be faster and better. But in order to understand how semi-classical dynamics works, I think it's good to have these models. In the moment that you have 2D, it starts to be comparable. In the 3D, already it's faster semi-classical than quantum dynamics. Okay? Basically, because semi-classical is local, so you only need the gradient, and quantum dynamics is global, so you need a wave function in all the space that you are propagating. So if I try to do the same with semi-classical dynamics, what I have is basically the same situation. So my laser pulse here populates the red state, and then after some time, the blue one starts to be populated. You can see that it's not exactly the same, but it's very, very similar. Okay? The main difference, where it is, when I consider all the trajectories, the main difference is in the nodes. Okay, here, if I do quantum dynamics, for example, in this case, I am creating a hole in the ground state, and then I am like creating the B = 1. You can see here the node in the ground state. Okay, I am not able to reproduce this in quantum dynamics, in classical dynamics, because I don't have vibrational levels here. So if you want to do this, it's not going to work. Okay, be careful. Because you can try, but it's not going to work. Of course, in the case of the excited states, if they are dissociative, there are no vibrational levels, and then you have basically the same solution in semi-classical dynamics and in quantum dynamics. Okay? But when you have some interference pattern, it's not going to work. So fortunately for us, when the molecules start to be very, very big, these interference patterns are less and less important. Except if you are interested in tunneling, very low temperature, and you want to pass a barrier. Of course, you will never do this in quantum dynamics because it takes forever. Okay? But even if you try, it's not going to work, because you are not able to do tunneling, because this is a quantum effect in the nuclei. Okay? So you cannot do it. And in this case, for example, you can see the nodes that you are not able to create in your semi-classical dynamics. Okay, not possible. Okay, another regime. What happens when my laser is very, very strong? Okay, if my laser is very, very strong, then the laser, since it's an electric field, can interfere with the electric potential, and the laser can be comparable, or the potential created with the laser can be comparable with the potential itself. Okay? And then I can do control. In this case, what I am going to do is a method that is called uplink, that is adiabatic partial by light-induced potentials. The idea is that I am going to use 2 laser pulses to create a path from going from one state to the other state. This is created in what is called the Floquet picture. Basically, the frequency of the laser is included in the potentials. Okay? And then I only care of the amplitude. So what happens then? Okay, I start here. I start to have one laser that increases. I create here a repulsion. Then the other lasers, I create another repulsion in the other part with the other laser, and I can move from one side to the other. What I am doing is I am creating with the lasers, I am creating a path. Okay? I am creating new potentials that give me a path from going from one well to the other well. Okay? And this we can do also with semi-classical dynamics. Okay? So again, you see the first laser creates here a repulsion between these two states, the second creates it here, and then you create a path that you can go from one well to the other well. Okay? This is quantum control. And you can do it with semi-classical dynamics, but it's very expensive. Okay? But in principle, you can do it. And this is the result of quantum dynamics. As I say, much cheaper, easier, because you don't have to do any trick. Okay? And semi-classical dynamics. Basically, you can see that I create here the path, and the wave packet, in this case, the trajectory is moved to the other side. It works. Okay. So, drawbacks. What is not included, or what I didn't explain to you up to now, of surface Hopper. So there are two things that I didn't speak about them, even if I include them in all the simulations that I showed you. Okay? One thing is the decoherence, and another thing is the energy adjustment. Let me call it this way. Okay? So which is the decoherence? If we check the model that we were seeing before, remember, we have the wave packet, moves, arrives to the conical, creates two wave packets. This is what, for example, AIMS do, no? One goes faster, the other one goes slower. Okay? I don't have this. What I have is a ball. What happens to the ball? The ball arrives to the conical, and now I have amplitudes. I have two amplitudes. The amplitude of the surface where I am running, and the amplitude of the other surface. Okay? So one amplitude is the blue, the other amplitude is the red. But both amplitudes are attached to the same trajectory. This means that if I am moving in the blue potential, the amplitude of the red potential is moving with a gradient that is the same as the blue potential. So this means that they are moving together. And this is not what happens in a wave packet. The wave packet in this point has to go faster. Okay? So somehow you have here, even it sounds strange because it's classical, an excess of coherence. My electronic wave packet is too coherent because it's not able to go in for two different gradients. It's only able to go in one gradient because it's attached to a single trajectory. So somehow you have to correct it. Okay? And there are several methods, but probably the easiest one, and the one that I implement because I'm lazy, is the one developed by Granucci and Persico in Pisa. That is called energy decoherence method. Okay? Which is the idea? The idea is the surface where I am not, I have to remove population. And then I am going to do it with an exponential. I forgot to cite. I have to put the site, sorry. It's a JCP of 2002, I think. Okay, basically, I will have that the coefficient of the states where I am not propagating, I'm going to use a damping function to remove them eventually. Okay? And this damping function is this one, and it's basically based on the fact that the energy in principle should be conserved. Then an hypothetical trajectory in the other potential will run with another velocity that you can estimate with the energy difference of the two states and the kinetic energy of the trajectory. And with a parameter that you have to invent, 0.1 watts. They test a lot, okay? They test 0.1, 0.2, and it works. They also do some more elaborated decoherence method, okay? There are a lot. You can use exact factorization. You can use one thing that is called AFFS, but I don't remember the acronym where it's coming from. So there are very different things. In fact, Granucci and Persico have a very nice paper that is a review of possible decoherence methods. Okay, I forgot to put it here. Okay, of course, if I remove population in the states where I am not, I have to somehow compensate it by putting populations in the state where I am. And in principle, this is done such as the sum is 1, if it's normalized, or the sum is whatever you want to have if you want to maintain the norm. This is something also very important, okay? If you use non-adiabatic coupling, they change very rapidly with the coordinates. Okay, and for example, in my case, I am using a Runge-Kutta propagator. This means that if my propagation is wrong, this will sign, I don't know how to say that in English, but it will be very, very clear in the norm, because the norm is not going to be conserved. So then I don't want to renormalize my wave function, because I prefer to know if I have everything correct. Okay, and this is something very important. So then, in my case, I also try always to maintain the norm, because if there is something incorrect, the norm is going to do, whoa, crazy things, and then you say, oops, I am doing something wrong. Okay? So, another problem. What happens if I don't jump exactly in the point of the conical intersection, or in the point where I have the degeneracy? Then, my wave packet, I will create, or my trajectory is going to run, not here, but here. Exactly in the same point, but in the other potential. Okay? And then I have to run here. Ooh, this is dangerous, no? Because the energy is not constant anymore. Because in the moment of the jump, I lose some energy, no? And if my jump goes up, I win some energy. That is even more dangerous. Okay? So then one has to somehow take this into account. Usually, you do it by rescaling some component of the velocity. So in principle, your velocity is going to be modified by some factor times a projector times the velocity. So this projector is the component, no? In principle, if you are very lazy like me, you can put the projector 1. This will mean that you are correcting the velocity in the direction where you are running. I have a lot of criticism of that, and probably they are correct. There is another option, but that requires to calculate the TACME. No? In principle, they say, okay, you don't have to correct this in all the directions. You have to correct this in the direction of the NACME, because the non-adiabatic coupling is what is sending you to the potential. So in principle, you should use the non-adiabatic coupling to correct. So you have to basically project your velocity in the direction of the non-adiabatic coupling, and then correct the velocity there. Okay? Why I'm not doing it? Because then I have to calculate the non-adiabatic coupling, and it's expensive already to do an extra calculation on top. Okay? Right. Sometimes, especially if you go up, you can have a problem. I mean, you don't have enough energy, so you want to go up. But even if you sum your kinetic energy and your potential energy, you have less energy than the potential energy on the top. And then what you do? So this is usually called frustrated hops. You are trying to go there, but you cannot. And there are different solutions. I go for the easiest one, as always, maintain the direction. So I don't do anything. I just have a warning, frustrated job. I try to go there, and it's not working. That's all. Of course, there are some people that say that this is equivalent to hit a wall. It's like you go to this state, but it's like close. So you hit like a wall, and then they say you have to reverse the velocity so that you go back. As I say, this is a trick. There are no a theory that sustains neither one, neither the other. It's not clear what you have to do when you have this frustrated hop. So in principle, I just maintain the direction and pray that this is correct. There is no good solution. Okay? So these are the corrections that we use for surface hopping. And with this, I finish the theory. There is any doubt, any problem? I was more or less clear. Wow, I'm happy. Okay, so up to now, and I think for explaining, it's very easy to do it with models, okay? But of course, the main idea of using semi-classical is to go beyond models, no? Because in a model, of course, you can do it even with quantum dynamics, or if you know the potential, shape, and everything, MCTDH is also working, and then you have really like the full quantum dynamics, no? So the idea of this method is not to work in molecular models, but it's more to work in real molecules. So I am going to put you just 2 examples. There are many more, but these ones, I did them, and this means that I have the figures. For the other ones, I have to collect them. Okay? So I am going to focus into methyl iodine. This was the reason to create or to develop this sharp methodology. Okay? Because when I came back from Jena, I had to do a proposal from Juan de la Sierra, and then at that time I was planning to come back to CSIC with Rebecca Denalda and Luis Pañares, and they are experimentalists, and they work a lot with methyl iodine. And all the things that I was doing in Jena during my postdoc are not able to work in methyl iodine. So then this is the reason to use sharp. Here is very important to use. This is nicer because Eva did it. It's a biological molecule. Everybody is very happy with it. You can sell it better. But I can tell you that in principle, you don't need to use this elaborated mechanism. Okay? You don't need to use sharp. You can use a regular surface copying and it will work again also. Okay? But let's see. So why methyl iodine is so interesting? Well, if I calculate the energy surface, the potential energy surface from methyl iodine, here I'm focusing the distance carbon iodine, and I don't consider the spin orbit coupling, I have this. The black ones are the singlets, and the red ones are the triplets. Okay, as expected, in the dissociation limit, the singlets and triplets are degenerated if you have a spin orbit. Okay? And then what you will have is, you can run in the singlets and the triplets. If you use the gradient, you will have more or less the same energy at the end. Okay? Now, which is the reality if I consider a spin orbit and I diagonalize the Hamiltonian at every time? This is the reality. So then, what happens in iodomethane is that these 2 channels are not degenerated. In fact, they are separated with almost 1 eV. Okay? And also, when you do this, you create a crossing in the region that is not observed here between the electronic states. So you have also a conical intersection. So the spin orbits is changing so much the landscape that when it was not conical intersection, now there is a conical intersection. And when the dissociation energy was the same for all the channels, now there are 2 different channels. Okay? So then, if you try to do regular surface hopping here, it's not going to work. Okay? So, what happens if I do this methodology? Then I have here 2 examples. This is potential. This is one example where I start in the potential 7. Here you will see the movement of the molecule. Here I will plot the energy. So I will plot the total energy to see that it's conserved because there are a lot of approximations there. So, and the gradient and the total energy are calculated in 2 different ways. So if the total energy is conserved, this means that the gradient and the energy that I calculated are at least compatible. Okay, so I like always to have some sort of safety net, no? Because you can do a lot of things, but it can be very dangerous. Okay, so if I start here in potential 7 and then I run, I start here, I see that the total energy is more or less constant. I arrive very, very fast to the conical intersection in the region. And in this case, for example, I go to the channel on the top. So I create the fragment in the red channel. The dots is where is my surface at every time. So which is the surface where I am running the surface coupling. Okay, you can see the energy is more or less conserved. I am very happy with this. Okay, now this is one example of trajectory where I don't put extra kinetic energy at the beginning. So I just do the Frank-Condon geometry, put it in the excited state, and let's see what happens. Okay? Now, if I use initial condition, as I explained you, then I will have something like this, a lot of movement. The total energy is now bigger than the potential energy here at the beginning. Okay, in this region, they go for a crossing. In this region, it's not easy to see. And in this case, for example, I also stay on the top. Here you can see all the problems, okay, because I don't want to hide anything. So the energy is not so nice conserved, especially in the region of the conica. Why? Because I am eating all the non-adiabatic couplings. And also I am not considering my pivot coupling has any gradient, okay? So it's dangerous, but it's not so bad, okay? It's not so bad. The difference can be less than 0.1. So if this is always the same, I will be very, very happy, okay? Now, can I compare this with the experiments? Even the time resolution. The time resolution here is very, very short, okay? So the conic intersection happens at around 10 femtoseconds, okay? So then Mañares proposed an experiment that they can do, okay? The idea, from the theoretical point of view, I'm not going to explain the experiment today. The idea is the following. I can run a lot of trajectories. Okay, here I have my kinetic energy, depending on the time. And then the colors is telling me which potential I am. You can see very, very bad things here. That is the correction of the energy. But it's okay, it's what you have. And then I can project these trajectories into the dication, in my case, and check the kinetic energy that I will win due to the Coulomb explosion of the molecule. And this is this here, okay? Where I put also the Coulomb explosion. So you can see this nice shape that is not the same as this, and this will be the kinetic energy if I include the Coulomb explosion in my model. Now, this they can do it in experiment. They can pump with one laser to the balance states, and then with some delay, they can use a strong laser pulse, go to the dication, and check the products that they obtain from the dication that are charged. Okay? And we can compare both curves. Okay, here, these curves that are moving, this is the experimental result. And these lines are the theoretical results. Okay? You can see that I am creating the wave bucket of the other state, in this case the white, here in this region. And I can see at which time this happens. In this case, it's 13 femtoseconds. And in this part, they don't have resolution, but you can see that the rest of the dynamics is exactly the same as the one that they have. So this means that with this technique, we were able to say exactly at which time the conic intersection happens, even if it's at 13 femtoseconds, okay? I am very happy. I am very proud of this because we sent the paper the 13th of December, they accepted it 17th of December, and it was published the 18th of December, okay? Without the referees. First time that this happens to me, and I think it's going to be the only one in my life, okay? The editor says, nice, publish as it is. And I say, shit, I didn't put everything. But okay, it works. I have to say that there are very recent experiments done in Berkeley in the group of Steve Leone, where they basically use X-ray, okay, and they try to do the same with X-ray, and the conclusion was, I think, 12.7. So the conical, they arrive at the conical at 12.70 femtoseconds, okay? So I think it's not so bad in the good track, okay? So this is one example where to use these techniques is very, very important, because otherwise you cannot do it, okay? So another example that is more exotic, and I am gonna just show a single trajectory from Eva's work, is prebiotic DNA, okay? The idea here is, let's study the 4-oxopyrimidone, well, no, 4-pyrimidone or 4-oxopyrimidone, sorry, 4-pyrimidone, and let's see what happens when you do 4-pyrimidone. So the same behavior, semi-classical spectrum, selection of trajectories, running of the trajectories. Okay? Eva did all the work. So basically 100 trajectories, 500 femtoseconds, In fact, she gave me the slides also. 73% of them return to the ground state in less than 500 femtoseconds, so it's very fast. 27% remain in the excited state, and from this you have 19 in the S1 and 7% in the triplets. In general, the sum of all of them. So with this, you can say that this molecule looks like photostable, a very fast relaxation to the ground state. Okay? However, if we focus in the trajectories that go to the ground state, Eva was checking one by one. I think Vasily already told you. You can say that 100 trajectories is a lot and everything should be automatized. But at the end of the day, you're going to check one by one. Okay. Check back one by one, and she found some trajectories that are very, very straight. So this is the trajectory, this is the movement, and this is the energy. So she observes how the trajectories go to the ground state in the region, but they break. Okay? So we were not very happy. We checked that everything was correct, and everything was correct. At least this is what we think. So it's very interesting because we try to understand this, and then what we say is, okay, let's check what happens if I try to connect with a lattice elastic band, sort of a MEP, minimum energy path, the conical intersection with these stable products. And if you try to do it and you optimize, they tell you, no, the only way that you can do that, or the minimum energy path for going from this conical intersection to these products is via the ground state minimum. But this is not what we see. We see a direct path going to here. So we ever analyzed the non-adiabatic coupling. So she has to calculate it. I always try to skip it, but she did it. And then she realized that the non-adiabatic coupling was related with the opening of the ring. This means that only the trajectories whose velocity is parallel to this vector are the ones that have more probability to jump to the ground state. And then this is a dynamical effect because you go to the ground state with a lot of kinetic energy in this direction. So the conical intersection decides how you go back to the ground state. The conical intersection decides the dynamic of your ground state. Okay? I don't know if here you're familiar, but it was a paper not time ago, and it started to be very old, on formamide that they demonstrate they call a new type of mechanism that they call it roaming mechanism. Okay, this roaming mechanism, basically the idea that they found in formamide that they can create CO with a rotational levels that are a little bit strange, and this was related with not a direct fragmentation, but like a travel of one of the fragments with respect to the other, rotating. Okay? And the only way that Bowman was able to reproduce this using semi-classical trajectories in the ground state, okay, was if he sort of biased the sampling in the ground state towards the region of the conical intersection. So something similar probably happens there. And with this, I want to finish. They told me that I should be on time. I am 20 minutes before time. So everybody should be happy, okay? So conclusions or take-home messages. Important things. You can recover quantum interference from semi-classical simulations. For example, you can mimic the vibrational levels with a bit distribution. This will help you to have a quantum distribution, at least in the ground state. You can include couplings, no adiabatic, spin orbit, laser, but you have to be very careful because you can do it in the electronic part of the Hamiltonian, but then you have to couple them with the classical equation running in a different states in the adiabatic ones. Okay? The idea of surface hopping or all these techniques that are semi-classical, at least from my point of view, that it can be biased or I don't know, is just you have to try to put as many quantum effects as you can in the electronic part. Okay? Because the electronic part is solved by the time-dependent equation. So if you put quantum effects there, you are going to have them, you're going to take them into account. Okay? And then try to left in the nuclear part the most classical things that you can. Okay? For example, in the case of laser pulses, you can do it with Floquet. So if you use Floquet representation, basically all this frequency that is going to affect your vibrational wave packets, creating a linear combination of vibrational wave packet. You remove it, and you put a more regular coupling, let's say, to run. Okay, and then, for example, in this case, you can do like this adiabatic passage by letting this potential, change of the potential by the laser, and so on. Okay. With this, I want to finish my acknowledgements. The sharp method was developed with the group of González when she was in the University of Vienna. The guy that programs the first version was Martin Richter, and I did my own version, and it was also both Philip Marquetant and González, and Ignacio Solá. The part of the adiabatic passage was done by Juan José Bajo, that is not in science anymore, but was a PhD that I had a long time ago, with the help of Ignacio Solá, in Universidad of Madrid. In the case of iodomethane, the experiment was done in the group of Luis Bañares, by Sonia Maggi, Rebecca Hernanda, and Mario Morales. And in the case of the 4-pyrimidone, I was not the only one doing the theory. The main responsible was Inés Corral, and who did the theory was Eva Bosch. And the experiments were done in the group of Carlos Crespo in Chile. Thank you for your attention. If you have questions, we have 5 minutes. Any question? Tell me.
In the case of DNA one, you have told that some part is going to the triplet state, right?
Mm-hmm.
So have you checked anything for the phosphorescence, like because inter-system crossing is happening? So
we never checked, but in principle it's possible, no? Because you can take the trajectories and you can evaluate the dipole moment, including the spin orbit. So basically you can diagonalize the component of the triplet of the singlet that you have and check it. We did it with some sort of transient absorption. Basically, we took the trajectories and we checked for every trajectory where are the rest of the states, and we calculate like a time-dependent signal. But we never did it for first. It would be very, very nice.
may I know what is the what time frame it was in the triplet state?
So the time that it took to go to the triplet state was very fast. This was corroborated by experiments. Okay? So it was very fast. So they go 137 or something like that. If I remember correctly, they checked, maybe not in this one issue, but in another one, they checked phosphorescence in the experiment, and they observed a long life state that was something like nanoseconds. Any more questions? Okay, then I want to have lunch.
Okay, so remember after lunch we meet in the class of the faculty to go together to the faculty of law, and then before I start the exercise we pay attention.